1/8 inch 6061 aluminum was used for the manufacture of the calf and knee parts of the brace. 1/4 inch 6061 aluminum was used to make the backplate of the hinge and the servo mounting plate, allowing the grooves to be machined within them. Other parts were nested in between them to create a stronger base to mount the other components to. Small stainless steel bolts were implemented into the double hinge mechanism for a smooth motion and the ability to withstand large shears during cycles. The skin interface includes a compression sleeve made up of a nylon polyester spandex blend, and the metal in contact with the knee has been sanded/filed down and padded to prevent injury while testing. In our design, we've been able to manipulate the knee angles via a slider moving by a string wrapped around the arm attached to a high-torque servo motor. We mounted the motor with parts manufactured from 1/4 6061 aluminum to the hinge backplate, so the length of the string does not have to be adjusted during knee bending. The mounting plate also mechanically prevents hyperextension past 2 degrees. By preventing the knee brace from hyperextending mechanically, we have provided a consistent safety feature for the user while testing.
The FEA simulation run on our prototype designs were used to show structural integrity from dynamic loading. To do this, the SOLIDWORKS model was exported as an IGS file and imported into ANSYS. In ANSYS, a rigid dynamic system report was run for deformation, shear, and normal stress, for both average operating load and 3 times operating load to show that the brace would be able to withstand average user under extreme conditions. The results were then compared to the material properties of 6061 T6 aluminum used for the brace and the 304 stainless steel bolts. In the shear stress simulation, the maximum force, which was in the pins, was 3.27 megapascals, which is less than the modulus elasticity for the steel used, which is 193 gigapascals. The normal stress simulation produced a maximum of 4.62 megapascals, which was lower than the modulus elasticity for both materials used. Due to this, it was determined that the brace would be able to withstand forces of at least 3 times the average intended user while under extreme conditions.
The electrical components for the design, including the Arduino Nano 33 BLE microcontroller and LSM9D-S1 inertial mass unit sensor and servo motor, have been implemented onto the physical brace as shown. Next, the brace underwent gait testing, which included collecting data while wearing the brace for a normal gait and simulated antalgic gait. During these tests, the brace was also restricted at different angles using the servo motor, which is controlled through the Arduino microcontroller. The arm of the servo is currently programmed to reach 3 different points of rotation. Each point of rotation causes a different angle restriction of the knee. The first setting allows the knee to bend between angles 2 to 30 degrees. The second setting allows the knee to bend between angles of 2 to 50 degrees, and the third setting allows the knee to bend between angles of 2 and 88 degrees. Programmable knee restrictions allow us to see changes in the gait cycle when the brace is restricted at different angles. Here is live positional data from the sensors during my normal walking gait cycle. Here is live positional data from the sensors during a simulated antalgic walking gait cycle. The data from gait testing has been compiled using Excel and shows that the brace successfully produces controlled restrictions at different angles using the servo motor mechanism. During antalgic gait testing, reduced restrictions led to an increase in knee angle magnitude, and unrestricted antalgic gait shows no significant difference in the subject's knee angles compared to restricted normal gait.